imagine for a moment you're not just looking up at the night sky, but you're actually listening to the universe. It's whispers, these subtle shifts in color. They're telling this profound, epic story. And what's really incredible is that it took two brilliant minds, one a priest physicist, the other a lawyer turned astronomer, to teach the universe how to speak its deepest truths through the very color of light. Today, we're embarking on a deep dive into the groundbreaking work of Georges Lemaître and Edwin Hubble. Their discoveries didn't just tell us the universe is expanding, they revealed this fundamental velocity-distance relationship that, well, it changed everything. And right at the heart of it all, redshift. That subtle shift towards the red end of the spectrum that serves as the universe's ultimate messenger. So our mission today is to unpack how redshift became this cosmic storyteller, not just through the lens we usually use, general relativity, which is, well understood, but also through a fascinating new framework. It's called motion theory. We'll explore what this means for our understanding of, well, pretty much everything, from the universe's expansion to its origin, and maybe even how it might offer fresh perspectives on some of these big cosmic tensions baffling scientists today. By the end of this deep dive, you'll hopefully have a really streamlined understanding of a topic that, it fundamentally reshapes our view of reality. It all started with this intriguing connection, almost like a silent conversation between Lemaître's abstract equations and Hubble's concrete observations, where the sky's redness learned to speak. So where do we kick things off on this journey?
We really need to begin with the pioneers themselves. And what's fascinating here is how two very different approaches, really different, converged on the same cosmic truth. On one side, you have Georges Lemaître, a remarkable figure priest, mathematician, cosmologist. As early as 1927, he was already tackling Einstein's field equations, but not just for a static universe. No, he found a non-static, homogeneous solution, what we now recognize as the FLRW model.
Right, the Friedmann-Lemaitre-Robertson-Walker metric. So he wasn't just theorizing in a vacuum, he was already thinking about a dynamic universe.
Exactly. And he didn't just find the solution. He actually derived a linear velocity-distance law from it, and even made an early estimate of the constant, the one we now call H. This was well before, widespread observational proof.
How? Before Hubble's famous paper?
Yes. And he even proposed the concept of a primeval atom, which, if you think about it, clearly foreshadowed what we now call the Big Bang Theory. He was really working at the theoretical frontier.
That's incredible foresight. And then the other side of the coin, Edwin Hubble, the observational powerhouse. It's quite a career change, isn't it? From lawyer to astronomer. Do you think that background influenced his approach? Maybe that logical training?
That's a great question. I think it probably instilled a really rigorous, evidence-based approach in him. Hubble was the one who definitively proved that those fuzzy spiral nebulae
that people thought might just be gas clouds in the Milky Way.
Precisely. He showed they weren't just clouds within our galaxy, but were, in fact, entirely separate galaxies, vast island universes way beyond our own.
Okay, and how did he bridge those immense distances? How could he possibly measure how far away they were?
He did that using Cepheid variables. These are stars that act as standard candles.
Standard candles, right, because their brightness relates to how fast they pulse.
Exactly. They have this really reliable period luminosity relationship. Basically, the faster they pulsate, the intrinsically brighter they are. This let him accurately measure distances to these incredibly far-off objects.
And this is where Lemaître's theory and Hubble's observations meet head-on. 1929, Hubble publishes his empirical velocity-distance relation, the Hubble-Lemaître law.
That's the moment. The standard synthesis, the story we usually tell, is that distance, d, and recessional speed, v, are related. Simply put, v is approximately h times d, at least for small redshift, z.
Right.
And that z, that redshift we observe, reflects the stretching of light's wavelengths as space itself expands. This is the common understanding, the one you probably learned.
That's the established view, yeah. The bedrock of modern cosmology. But our deep dive today promised something more, a new lens. What exactly is this motion theory? How does it rethink reality?
Okay, so motion theory, or MT, offers a fundamentally different framework. Its core idea, and this is the big shift, is that reality is structured motion synchronizing under constraint.
Whoa. Okay, say that again. Structured motion.
Structured motion synchronizing under constraint. So instead of thinking of reality as things happening in space and time, think of reality as the structured motion itself, the dance, not the stage.
That's a big conceptual leap. So if reality is the structured motion, how does MT redefine things like space and time, even gravity?
Well, in MT, space isn't an empty box. It's unresolved motion. Think of it not as emptiness, but maybe as this subtle underlying hum of activity that hasn't yet organized into a specific thing.
Okay. And time.
Time becomes a comparative resolution rate between different systems. It's essentially how quickly one system clocks its internal motion compared to another. It's relational.
And gravity, you said it's convergence toward higher synchronization density?
Exactly. Picture objects naturally moving towards regions where their internal clocks, their structured motion, can more easily align and synchronize with the surrounding motion, more easily keep time together. That convergence is what we perceive as gravitational attraction.
Like a kind of universal tendency towards harmony or efficiency. That's a really interesting way to put it. What about light then, our messenger?
Right. Light. In MT, light is described as synchronization events propagating at the maximal resolution speed. And that speed, c, is fundamentally related to the structure of reality itself. Specifically, c equals the square root of s over r.
S over r.
Where s represents structuring or organization, and r represents relaxation or disorder. So the speed of light is tied to the inherent organization, the sort of sync density of reality.
Then a photon.
The photon isn't a tiny particle, like a pellet. It's more like a phase-locked packet of alignment that's moving through this structured motion.
Yeah.
And the frequency you observe, that's basically your detector's sync rate with that incoming packet of alignment.
Okay, so if light is about transferring alignment, then redshift isn't about stretched wavelengths in the same way.
Not exactly, no. In motion theory, redshift becomes cumulative rephasing. Imagine light traveling across cosmic districts with different levels of this synchronization density, different SR values.
Okay.
As it crosses these regions, the alignment ledger, you could say, rebalances. If the past trends towards lower overall ordering, or passes through gradients that sort of tax its coherence, your detector reads a lower sync rate.
Which we see as redder light.
Which we perceive as redder light.
Exactly. So cosmic expansion itself gets reframed. GR says the scale factor, AT, increases, stretching wavelengths. How does MT explain the observation?
In MT, it's the background ordering field, the net SR across the cosmos, that relaxes over cosmological time. It becomes, let's say, less densely ordered overall. This relaxation leads to a systematic reduction in the encountered sync rate for light traveling vast distances. It produces the exact same observed redshift effect as stretching wavelengths.
So the math works out the same, the observables match.
The observables match, but the underlying story is different. GR talks about the metric stretching. MT talks about the alignment budget rebooking as the background resolves or relaxes.
That's a really crucial distinction. Same numbers, different narrative. Okay, let's connect this back to Lemaître's equations, his FLRW solution. How does motion theory interpret those foundational equations?
Right. Lemaître's FLRW line element, which captures that large-scale homogeneity and isotropy. MT recasts it. Instead of a scale factor AT representing spatial stretching, MT talks about a global sync density. Let's call it NT. This AT basically sets the local speed of light, c, and dictates the rules for comparing sync rates over cosmic distances.
And the Hubble parameter, HT, the expansion rate.
In MT, that corresponds to a global drift rate in ACK. So where GR encodes curvature, MT encodes how the allowable alignment budget, the SR ratio, changes with cosmic epoch. But crucially, both frameworks give you the same linear relationship. Z is approximately at GTC at low redshift. First order, they agree.
It's like translating between physics languages. What about Hubble's ladder, then? That whole process of using standard candles to measure distances? How does MT view that?
Well, those standard candles, like the Cepheids Hubble used, are seen in MT as self-clocking structures.
Self-clocking?
Yeah, their period luminosity relation is interpreted as an inherent sync law. It's a stable way these structures organize their internal motion, their internal clocks. So when we build Hubble's ladder, climbing from nearby stars out to distant galaxies, each rung represents a transfer of synchronization across scales.
From stars to clusters to galaxies.
Exactly. All bridged by the physics that dictates how these different clocks keep count relative to each other. The Hubble plot itself, distance versus redshift, becomes this grand ledger, distance versus accumulated rephase.
Distance versus accumulated rephase. I like that. It shifts the focus from stretching to, well, bookkeeping of alignment. Okay, so if redshift is this cumulative rephasing, does MT give us a cleaner way to categorize different types of redshift, beyond just Doppler or cosmological?
It does offer a unified perspective. MT naturally delineates three types, all under the same umbrella of sync rate comparison. The first, you have Doppler-like redshift. That's simply local relative motion changing the encountered sync rate, how frequently your detector samples the alignment packet. Pretty straightforward.
Okay, makes sense.
Second, gravitational redshift. This is framed as climbing out of a deeper sink density well. Near a massive object, the sink density, SR, is higher. Clocks effectively run slower there, relative to an observer far away. So light climbing out appears to have a lower frequency, a lower clock rate, when measured far away.
Like time dilation due to gravity, but explained through sink density.
Precisely. And the third type, cosmological redshift, the one tied to cosmic expansion.
Yeah, how's that framed?
In MT, that's the cumulative drift of the background ordering along the light's entire path. While GR describes it with the ratio of scale factors, 1 plus z equals a, now a, MG describes it as an exponential integral related to the change in SR along the path.
But again, the final number, the calculated redshift z, is the same.
The number comes out the same. Same observable, different conceptual story about why it happens.
That's key. Now, a critical question. Does motion theory accidentally revive the old tired light idea? That light just loses energy somehow. Because that hypothesis had major problems.
No, absolutely not. That's a crucial point. Any valid redshift mechanism has to reproduce other key observations, specifically surface brightness dimming, the Tolman test, and the time dilation we see in supernova light curves. Distant supernovae appear to explode in slow motion.
Right. Tired light couldn't explain those.
Exactly. MT's rephasing picture preserves both. Why? Because it's fundamentally a clock rate effect. It affects the timing and perceived frequency based on synchronization, not some kind of energy loss like light traveling through a fog. So it naturally incorporates time dilation and passes the Tolman test.
Okay, that's a vital safeguard. It keeps the observational successes intact. Let's circle back to Lemaître's primeval atom, that idea of a hot, dense beginning. How does MT recast that?
Lemaître's brilliant metaphor is reframed in MT as an epoch of extreme ordering pressure, a time when the SR ratio is incredibly high. In this state, small regions would have rapidly phase-locked, creating this highly organized, intensely synchronized state. Then as the universe evolved, this state began to relax towards lower overall synchronization density. Structures started to form.
So the bang isn't quite an explosion, but more like fast ordering followed by redistribution. A relaxation.
Kind of, yeah. Fast ordering followed by redistribution is a good way to put it. A phase transition from extreme sync density towards a more structured but less intensely synchronized state.
And the cosmic microwave background, the CMB, that afterglow light?
The CMB, in this view, becomes the fossil ledger of that phase transition. It's the imprint of that nearly uniform sync background from when the universe became transparent, with those tiny alignment ripples, the anisotropies we measure, showing the seeds of structure.
This reframing, could it shed light on current problems, like the Hubble constant tension, where measurements of the expansion rate today seem to disagree with predictions based on the early universe?
It might offer a new angle, yes. It doesn't provide an instant solution, but it gives us a clean target for investigation. MT prompts us to ask, are we correctly assuming a perfectly uniform sync landscape across cosmic time and space, especially in the late universe where structure is very clumpy?
Meaning the local environment could affect measurements.
Potentially. If the local synchronization density around our standard candles like Cepheids or supernovae is slightly different depending on their host galaxy environment, maybe its metallicity or density, if that correlates with you and I, it could introduce a subtle bias in our inferred distances.
Without needing to change the physics of the early universe CMB?
Exactly. It points towards questioning assumptions about the late-time universe's uniformity and how it might affect our rulers, rather than necessarily a fundamental conflict between early and late physics. It's a specific thing we could look for.
That's a very interesting angle. And you also mentioned redshift environment couplings.
Yes. MT predicts there might be subtle correlations that standard cosmology often treats as, well, just noise or nuisance parameters. Things like spectral line widths or maybe time lags in signals from quasars could potentially correlate with properties of the host galaxy environment that reflect its ordering or sync density.
So things we currently might just try to model out?
Might actually contain physical information about these sync rate offsets. They could be signals, not just noise, if MT is on the right track.
Okay, this is moving beyond just theory. It's pointing towards real, testable predictions. What kind of experiments or observations could actually test these ideas, sharpen the picture?
Right, this is where the rubber meets the road. MT suggests several concrete tests. One really cool idea is a phase index cosmic analog.
In a lab?
Yeah. Imagine building a special kind of waveguide, a metamaterial, where you can precisely control the effective SR ratio along its length, create a controlled drift. You could then launch phase-locked pulses of light down this waveguide and measure if they exhibit a redshift that matches MT's prediction for cumulative rephasing. It'd be like a tiny, controllable universe on your lab bench.
A lab-scale cosmological redshift. That's wild. What else?
Another approach is a clock network Hubble diagram. We have incredibly precise atomic clocks now, optical lattice
Yeah.
clock. Imagine deploying these, or using astronomical objects with known stable periods as clocks in different galactic environments. You'd look for tiny but systematic, environment-dependent sync shifts, differences in their perceived rates that correlate with the host environment's properties, its estimated sync density.
A direct test of the environmental influence. That sounds incredibly challenging, but powerful if detected.
Very challenging, yes. Then there's the supernova time dilation audit. We know MP must reproduce the observed 1 plus z stretching of supernova light curves. That's a given. But we could reanalyze the data explicitly through the lens of a detector source sync rate comparison. Check rigorously if the same rephasing rule consistently explains both the redshift of the supernova spectrum and the stretching of its light curve shape. A consistency check within the MT framework.
Got it. And you mentioned lensing earlier, gravitational lensing.
Yes. MT recasts lensing not just as light bending due to curved spacetime, but as light following least resistance alignment paths through varying sync density. This might predict tiny additional differential phase delays for light from multiply-imaged quasars, where we see the same quasar multiple times due to lensing. These delays would be beyond what standard GR geometry predicts. Detecting them would be very subtle, but potentially a unique signature.
Okay, so lots of potential avenues for testing. Let's just take a step back. It's important to remember what Lemaître and Hubble got profoundly right. Motion theory isn't about discarding their legacy, is it?
Not at all. It builds upon it. Both Lemaître and Hubble were fundamentally data-first scientists. Lemaître developed his equations but constantly checked them against the astronomical data available. Hubble, coming from observation, built his methods and laws directly from what the sky was telling him. MT absolutely inherits this data-first approach. It offers a new grammar based on invariance, alignment rules, sync rates, but it must always be validated by observation, by the ladder of calibrated comparisons Hubble pioneered.
And the fact that the simple linear Hubble-Lemaître law works so well at low redshift, that basic V exists H-0 relationship.
That success is crucial. It confirms that, at least to a first approximation, the universe is homogeneous and isotropic on large scales. In MT terms, it means the leading order drift in the global sync density is uniform enough that one single parameter, H-0, captures the dominant effect, just as Lemaître predicted and Hubble observed.
So MT isn't replacing GR or standard cosmology. It's more like offering a deeper translation, a different underlying mechanism for the same observed phenomena.
That's a good way to think about it. It primarily adds a single, unified cause language. Phenomena like redshift, time dilation, lensing, even the notion of expansion itself, they all become different manifestations of one underlying principle: how alignment is conserved while the background ordering or sync density evolves.
A unified story instead of separate explanations.
Exactly. It provides a potential way to talk consistently across scales, from tiny lab experiments potentially mimicking redshift, up to the largest structures in the universe, using the same fundamental concepts: SR, alignment high, sync rate comparisons.
And it suggests new places to look.
Yes, new cross-checks. It encourages us to look for subtle, coherence-sensitive observables, things like phase noise and signals, spectral lags, maybe correlations between different spectral lines, things that should track redshift or environment if the ordering of the path of light travels truly matters in the way MT proposes.
Okay. Now, with any new perspective like this, misconceptions can creep in. Let's quickly swat a few common ones. First, expanding space pushes galaxies through some kind of ether.
Right, the ether misconception. It's important to be clear. There's no ether. In GR, it's the geometry of spacetime itself that evolves.
Right.
In MT, it's the background ordering field, the sync landscape that drifts or relaxes. In both cases, physics remains local. Objects aren't being pushed through anything, and the speed of light c remains the local speed limit.
Good clarification. Second, redshift proves light loses energy during its flight. The tired light idea again.
No, we covered this, but it bears repeating. It's not about energy loss. It's about the detector source sync comparison changing due to the evolution of the background ordering along the path. The observed frequency changes, reflecting a change in relative clock rates or sync rates, but the local speed of light is always c. The photon doesn't get tired.
Okay. And finally, the big one. Motion theory denies standard cosmology. Does it throw out The Big Bang, Hubble's law, all of that.
Absolutely not. Let's be crystal clear. MT aims to preserve the observational successes. It keeps the Hubble-Lemaître law. It reproduces supernova time dilation. It's consistent with the CMB. What it offers is a different interpretation, a motion-first foundation, and crucially, additional testable predictions that could potentially distinguish it or refine our understanding. It's an alternative explanatory framework, not a denial of observations.
So, if we recap, Lemaitre taught the universe how to evolve dynamically. Hubble taught us how to measure its vastness, how to count its expansion. And motion theory, perhaps, allows that count, that redshift, to mean something profoundly deeper. The sky's redness isn't just a passive consequence of stretching space. It might be the active trace, the ledger of alignment conserving itself, while the universe's background synchronization density slowly, majestically changes over cosmic time.
That's the essence of it. We keep the data. We keep the successful predictions, the curves on the plots, but potentially we gain one coherent story. Maybe motion's the fundamental substrate, geometry is its emergent map, and redshift. Redshift is the universe whispering to us how that map gets drawn and redrawn in real time.
So, thinking about all this, what does it mean for you listening right now? Consider this. The very fabric of reality, from the tiniest quantum interactions, maybe, right up to the grand cosmic expansion we see. It might all be telling us one consistent story, a story rooted in fundamental motion and synchronization. What other deep connections, what other insights might we uncover if we keep listening closely to these whispers from the cosmos? And if we're brave enough to explore new frameworks like motion theory that challenge our deepest assumptions about what reality even is, we've really only just scratched the surface today. The journey of discovery, as always, continues.